And so now, Angela Biddle, our beloved Patreon, we have people at Gabversity, we have people at Gabsmacked, we have people at Gabsmacked on YouTube, hey, and we're about to start our podcast. Hello, our Gabsmacked podcast, which you can find on Stitcher and iTunes under iTunes/Anchor podcast/Gabsmacked. Same with Stitcher. You can find them on Spotify, I'm pretty sure, but that's a lucky guess. We'll see how we go. We're also here at Gabsmacked and Gabversity, and of course, Gabsmacked on YouTube. It's a pleasure. Rada is here at Gabversity. We have the owl. Pompous is looking at me from behind. Oh God, don't give me that image, Gabsmacked, you loser. And we have here Michael Aud on Gabsmacked. On YouTube, we don't know who will be there by the time this is uploaded. And we have our beloved podcast, which also has its own dedicated listenership. So hello to everybody. And what we were talking about earlier was the difference, bitches, between an emergent force and a fundamental force. Now, fundamental, really, how far back can you go? Well, we can only go as far back as we know we can go. Now, so therefore, something that is emergent, it just means that if we go deeper into it, it's actually not there. It's a result of something else. And as we said before, we could look at food as fundamental, but actually food, what we now, multi-platform broadcast, of course, yes, food is an emergent property of someone who makes the food. But we call it food, even though it's not really food. We eat it, but it's an emergent property. That's a very bad analogy, but we're getting there. The next analogy we provided in our last scope, everyone here on all of our broadcasts, I thought I was going to get sick of looking at my face. Now I have to look at it 3 times at the same time. I'm sort of like a multi-headed dragon. It's a bad analogy, yes. Someone at Gabversity said it's a bad analogy. Now, by the way, Gabversity is where we find our engineers. So you can expect that type of comment there, which is always fun. Always keep me in check. Now, what is the point of this? Well, as we said before, an emergent phenomenon is something like the wave, as they call it in America. In Australia, we call it the Mexican wave, because here we're a little bit, our culture is slightly delayed to catch up to you guys. But the wave exists only from the person making the observation of the wave outside of the crowd. If you're in the crowd, you can't see the wave unless you're at one end of the crowd looking at the other end. But once again, you're actually outside of it in terms of the domain of a certain place where the wave can function. So the wave is a consequence of the fundamental beings being the humans raising their arms and dropping their arms. It's relative versus absolute vision. Yes, extrinsic is right on the money with that one. So what does that mean? Well, the same thing is we have the same problem with temperature. Now I'm going to get to, all of this is going to lead to why we have a problem with gravity and quantum mechanics. And then from there, I will talk about dark matter, which has been the research of mine for the last 12 months, and quantum dark matter specifically. A topic about which I shall be possibly giving a speech next year at the Theoretical Mathematics and Physics Seminar sponsored by ANZ and AMP in a place in Australia called Merimbula. How you going, buddy? I'm from Merimbula. Give me your beer and grab your Sheila. We're going to go down there. What are you? Soccer's for girls and for poofters and pansies. You got to play rugby. Alrighty, that's actually one of my characters, but I can't find a kangaroo because my character is called Kanga with the last name Roo. Focus. Yes, I'm not good at focusing. I can't find the talking puppet for that. Seems to be sold out from Folk Manus, which actually makes the puppets. So, let's getting back to our beloved person that's telling me to focus, which is like Eagle. Focus, Gab. You will find a kangaroo. Alrighty. So let's get back to temperature. Temperature is also an emergent phenomenon. It's something that we notice on a macro scale, but when you drill down deep into what makes it up, it's actually not there. Sarah Ballerina, good to see you. And what do I mean by that? Well, if you look at, say, warm water, well, it's still water. What makes it warm? It hasn't changed its constitution, but it is, of course, the movement of particles. It's what we call kinetic energy, which is the amount that they're moving. That means that they're carrying an extra bit of energy, which actually makes it heavier, because mass is, of course, energy. Yeah. Good question. Rada just said you've wondered about that. Yeah. Well, warm water, it just feels warm to us, but what's happening is that the individual particles are vibrating at a higher rate or with more energy or with increased kinetic energy above its minimum energy levels. And that extra energy right? If you zoom into one particle, you're not going to notice. It's just a particle moving around. You have no idea how many other particles are moving that way, if it's just one particular particle, whether you're even moving quickly with respect to other particles, you wouldn't know, right? Same with this human wave. You just see a guy stand up and sit down, or a girl stand up and sit down, or whatever, right? It's all relative, exactly. Well, it's relative, and then we have something called fundamental, which is something that we cannot get further past, but that would still relatively be relative, I guess. So what is the issue with that? Well, if you zoom in to the water is still the water. It's vibrating in a different way. Boss Briggs is on Gabversity, one of our Patreons. And when you zoom out, it gives us the effect of because the group is collectively moving with an increased amount of energy, we feel that as warmth. So the point is that temperature is an emergent phenomenon. It's based upon a more fundamental phenomenon which has nothing. It does not act as if there is a temperature. It's related to kinetic energy, but we feel it indirectly as temperature. So this indirect feeling, or a derivative feeling, we call that an emergent phenomenon. That's versus something that's fundamental. What is the point of this? Well, we have a problem when it comes to gravity. Einstein described gravity as something that you can call wrapped, intrinsic to space-time itself. Someone just asked if there are no certain temperature particles. No. A particle itself doesn't possess a temperature. Dennis Hans is here at Gabversity, an astronomer. Guys, follow Dennis, capital R Hans. He's on Gabversity at the moment. You can see him there. He talks about astronomy on a macro level. I talk about things at a quantum level. So there you go. It's a good teamwork. Now, coming back to what we said. Yes, an individual particle, it doesn't make sense for it to have a temperature. No. You are extrinsic. There you go. Hey, Tiki's here too. So, what are we talking about? Well, Einstein depicted gravity as something that, quantum is spooky, something that is intrinsically connected to space-time. And space-time is this four-dimensional block which bends and twists depending on matter/energy, or mass/energy, which is the same thing in the theory of relativity. And this mass and energy intertwine. Depending on, there's a conversion, as you guys know, is called E equals mc squared, which is part of a greater equation called epsilon mc squared, and epsilon is based upon something called, if I can remember, now I can't even remember, it was, now it's gone out of my head. Hello, Autistic Savant, good to see you again. And let's have a look at how you're going. Wow, you've gone up to 38 followers and 13 following. Very cool, Bananas. Good to see you again. Lighting is better on Gabversity, everybody is saying. So sorry to our YouTube and Gabsmack guests. And those on our Anchor podcast won't even care. So there you go. Now, I don't even know what we were saying, but we can try and get back to where we were. Let me pause YouTube and regroup. Okay, we're back, everybody. All right, ladies and gentlemen, we're back. We were talking about the Lorentz Transformation. And Einstein was wrong. Einstein is wrong, but he is less wrong than anything else we can come up with at the moment. Epsilon is something called a Lorentz Transformation. And the Lorentz Transformation really is just to compensate for things traveling at different speeds. So we won't get into that here. For those who are on Gabversity, research the Lorentz Transformation. It's simply a mathematical transformation which can provide some sort of equality between things that are traveling at relativistic speeds. Because as we know, the faster something goes, the more force is required to actually have it accelerate, because it literally gets heavier and it accrues with it more mass. Now, I'm going to get into that later with our quantum particles. Quantum particles have something called a mass, but it's not exactly determined, and I'm going to get into that later on. It's got something to do with the uncertainty principle, but we'll get into that later. What is the point of this? Well, we don't know if gravity is emergent or fundamental. Now, there's a few reasons for that. One is that space-time is not the complete answers. They have spinners. You are 10 steps ahead, Autistic Savant. You should jump onto Gabversity, where our conversations will get slightly more technical. So, I don't even remember what we were saying now, but space-time itself is not the complete answer. And we know that. Why do we know that? Well, there are things that this mathematical construct of space-time does not answer. It does not answer what happens with black holes, and it does not explain what happened with whatever was before, if there was something before the Big Bang. And what happens with the mathematics of that is that it develops things called infinities. There's a mathematical term for that called a pole, and it is a pole that cannot be removed. There are different types of poles, and I know people are going to make jokes about that. Astronomy and physics, in general, is full of euphemisms. I don't know what the physicists were thinking of, and mathematicians. But if any mathematician here has studied complex analysis, Feynman trick was yes and no. That was a way to simplify the mathematics for other reasons, but it also had a benefit of simplifying a lot of the poles. Do I think parallel worlds are real? Parallel worlds are mathematically real. Whether or not they're actually real and in terms of existing, that's something that I guess, there's still an open debate on that. It would make a lot of sense because we used to wonder if there were other galaxies. Before that, we wondered if there were other planets, or the other way around. We wondered if the Earth was the center of the universe. Then we realized there was a sun. Then we realized there were millions of other suns. Because of time. Time is also a construct. It's something that we have designed to try and understand what is going on around us. But time has a specific location in Einstein's theory of relativity. Each point in space-time. Don't be a slave to math. Interesting. Each point has a point in space-time. It's a four-dimensional point, denoted by X, Y, Z, and W. It doesn't really matter what we use. But the issue is that when you zoom down into the quantum particle, time doesn't actually make sense. And time can also be transcended by something called the non-local principle, which I'm not going to get into today either. But the non-local principle, if you look that up, is where research is getting much heavier into that now because of something called quantum entanglement, where it's actually been proven hundreds, if not thousands of times, that particles somehow can have information shared between them that can travel faster than the speed of light. Not just faster, but instantaneously. In fact, they've done measurements where it's sort of been 1,000,000 times faster than the speed of light. Now, that translates to information traveling backwards in time. That sort of doesn't make sense from a causality type of understanding, but we won't get into that here. That's like a massive thing. We've only got 3 people at Gapversity. Maybe when we're finished the major scope, I'll go to Gapversity and talk about the mathematics of it. All right, so there is something more fundamental. So because the mathematics doesn't allow us to understand what's happening beyond the event horizon of a black hole, and we can hypothesize, but there's something that doesn't make sense, the flux capacitor. There's something called a Schwarzschild or Schwarzschild radius, and it is something that we can see mathematically. It's that once you shrink a radius down to a certain space and you have enough energy in there, you sort of rip the fabric of space-time and turn whatever you're looking at into a black hole. Because when you need to observe something, it requires energy. And of course, if you want to look at the smallest possible point, then the amount of energy you need to look at that point is going to be too much for that point and rip a black hole into whatever you're looking at. And so it becomes impossible to look at the smallest part of space-time. It's sort of, if we're in a software system, then it's sort of been designed that we can't look deep enough into what's going on. So we can't see what space-time is, or if that is the most fundamental thing, and for that reason, we can't tell where gravity comes from. It doesn't show up in quantum mechanic equations. Quantum mechanic equations, we're talking about waves, and it doesn't really make sense as to where gravity fits in that. Some people have hypothesized that gravity is actually motivated by something called a graviton, which would be a fundamental particle, which would make gravity a fundamental force. Some people talk about gravity being wrapped with space-time, but we don't know what's further beyond that, if it is fundamental or if it's emergent. And of course, somebody in 2010 from the Netherlands, whose name I forgot, but it will come back to me at some point. I think it's Erik Verlinde, there you go, came up with an idea called emergent gravity or entropic gravity, explaining that gravity is a consequence of something called the holographic universe, being that the universe, in fact, is a coded type of machine which projects into itself a 3D world from holograms from the outside of the edge of the universe, pushing it all in. And that act of sort of plotting that 3D information actually causes ripples and rips, which creates this gravitational effect in a very, very simplistic way of explaining it. There is an interesting concept about that, which is that black holes happen to have the surface area that would equate exactly to the amount of quantum bits that would have fallen into that black hole. And that's a very, very, very unusual coincidence. And so the holographic principle, has some legs to it. And so you would think entropic gravity works. Now, the issue with entropic gravity, number one, it predicts the Einstein field equations. It also predicts modified Newtonian dynamics. Now, what's modified Newtonian dynamics? That was created or invented. It's another one of those narratives or fake news, as we like to call it, because in physics, everything is fake news. In other words, we're all trying to develop narratives that explain what we're seeing, and no one really knows. As we said, Newton came up with something. 200 years later, we found out he was wrong. Einstein said, actually, that was only part of the truth. This is the actual truth. And now we know that Einstein's not giving us, or hasn't been able to give us the complete truth, but no one knows what is the more complete version. Some people are arguing it's string theory. Some people say M theory, etc., etc. Now, what is the point of talking about that? Well, this comes to dark matter now, but I'm going to quickly touch on modified Newtonian dynamics, also known as MOND. Now, MOND was a narrative created by Professor Mordechai Milgrom of Israel in 1983. And what he did was develop a mathematical construct for the true equation, what he believed the true equation of gravity was. And his equation fits with what we observe because gravity behaves very differently once you get onto the galactic scale, or there's mass there that we don't know about. That's going to be our dark matter topic. Now, the problem is that Professor Milgrom developed this mathematics based upon his observations, not from theory, like Einstein did. So we don't know why gravity is the way it is when Professor Milgrom talks about it. Professor Milgrom made observations about the fact that stars were orbiting galaxies way too fast. They should have been blown out of the galaxy, but they weren't. So a lot of people thought it must be this invisible matter we call dark matter, which is sort of warping gravity to pull everything in. But Professor Milgrom said, no, actually gravity behaves differently to the way we think it does. Newton didn't give us the full story. Einstein didn't give us the full story. And so it actually moves like this, which is a larger equation. It has something analogous to the epsilon, which is alpha naught. And that is something which actually, on a larger scale, warps gravity to make it behave in the way that we observe at galactic levels. Now, the funny thing is about that is that Erik Verlinde, who came up with the concept of emergent gravity in 2010, actually was able to derive from his theory both the Einstein field equations and Professor Milgrom's equations, both of them from the same theory. That's pretty freaky. Why would someone's theory, some random theory, generate the exact equations that Einstein came up with and Professor Milgrom came up with? You would think that that would explain it. The problem is it doesn't explain it, because our observations that we have developed are not completely consistent with dark matter, nor are they completely consistent with modified Newtonian dynamics. So where are we at? No one knows. Why am I bringing this up? Well, my professor came up with an idea in 2009 that quantum mechanics doesn't just govern the quantum. It doesn't just govern the little quantum that we can't see, which sort of work on a quantum level, which is, in other words, they're discrete. They have jumps in their movements. They move digitally, you could call it that. He hypothesized that it also works on a galactic level. Now, what gave him this idea? Well, someone called Professor Nesvehevsky in 2002, I think it was, as I said on my last scope, dropped neutrons in the same way you might drop a tennis ball, in the same way Galileo dropped rocks, as the myth goes that he dropped rocks. Dropped rocks, another not euphemism, everybody. All right. So when he dropped them and observed them in a gravitational field, you would expect that they would float down towards the Earth because they have a little mass, and so they would fall down a little, at a little speed. But that's not what happened. What happened was that they fell quantum mechanically. They actually fell in the same way. If you look at traffic lights, traffic light goes green, then it goes yellow, then it goes red. Rewind it, it would go red, and then turn off and then go yellow and then turn off and go green. So it looks like the light's traveling down, but it doesn't travel through the gaps. It sort of appears, disappears, appears down here and disappears, which is what's happening at the quantum level that we know of. So that's what's happening at a macro level with neutrons. Neutrons in a gravitational field are moving this way. And the professor said, so why could it not be that electrons that are orbiting particles that are gigantic, the particles the size of the galaxy, why could they not be doing the same thing? They just have so much energy pumped into them that each atom is spread out so far that it's the size of the galaxy. In other words, you have an electron that's orbiting a galaxy, for example. And there's so much energy in that. We're talking, what's 34? So a billion, 10 million times the energy of a regular atom. That's something called a Rydberg state. A Rydberg state is when you get an atom and inject so much, you pump so much energy into it that the electron that's orbiting the atom, well, it's not actually orbiting, but we have been raised to think it's orbiting. So let's use that for a second. But the electron that classically is orbiting the atom is so far from the atom that the material vanishes. It looks invisible. It's almost pure energy, you could call it. This energy is still mass. It's equivalent to mass. It's related by E equals mc squared or epsilon mc squared. So that amount of energy in there is warping space-time. It's warping it to the point where it's creating what we think is this gravity, this illusion of gravity, this warping of space-time. So, it's doing this, so we think we're in this, this gravity where Einstein predicted that light would bend, and light doesn't have mass. So if gravity was affecting only mass, then that means that light should not be bent, but it is, because it's ripping space-time itself or warping it. So basically invisible mass. That's what my professor has hypothesized, yes. So I spent the last, 8 months on and off because I had other stuff going on. So about 5 months doing thousands and thousands and thousands and thousands of pages using, of course, algorithms. Otherwise it would never have gotten done, of mathematical calculations to test whether it should be exactly as it is. And it turns out that it is exactly what we would expect, that if you pump enough energy into these particles, that these particles would orbit at the size of a galactic halo, which is the halo around a galaxy that's invisible, that people think is made up of dark matter, and that this would warp gravity in such a way that when the Big Bang happened and everything exploded, this amount of energy was warping space-time into buckets, and those buckets would collect the matter which allowed it to condense and form galaxies. Because that's the only way, well, not that particular hypothesis, but dark matter or quantum dark matter or modified Newtonian dynamics is the only way we could exist right now. Otherwise, at the Big Bang, everything just would have been Napoleon blown apart. For those of you who don't know the joke, Napoleon's last name was Bonaparte. So it would have been Napoleon blown apart. If you get a ball and you blow it up, it's going to blow all the way out. It's not going to coalesce and come back and go whoosh and come back in again, unless you use some magic Harry Potter wizardry and suck it all back in. How is this similar to the electric universe theory? I don't know enough about the electric universe theory to actually comment on that, but I will look it up and get back to you. So what's happened is that you need something that's immune to explosions, okay? You need some star and galaxy seeding. Okay, so yes, this idea, the consequence of this hypothesis is and would be that this type of energy was immune to the explosion, and this energy obviously had gravitational warping of space-time, so it actually warped the visible matter into coagulating and coalescing into galaxies, which then, of course, became stars and everything else within the galaxy. And the residual amount of that is what we see today as dark matter. Now, the professor hypothesized that there should be, based upon his hypothesis, a supermassive black hole at the end. Thank you for the super hearts. They are useless for us in Australia, but thank you anyway. You can always become a Patreon member at Gabsmacked, if you so wish, as Angela Biddle and other awesome people have done. So, what are we saying? We're saying that the professor postulated that there should be a supermassive black hole at the center of every galaxy that has dark matter around it. And it turns out that thanks to something called the Carr's hypothesis, and a few other observations, that is now proving to be exactly correct. So once again, his story could be completely wrong because it's completely radical, which is why I liked it. But it completely fits thus far, subject to further testing. Now, I've been researching it now this year, and so my findings are exactly consistent with what you would expect. And this could actually explain dark matter. If that is the truth, then we now don't have to look for dark matter particles because we've been looking for 50 years and have found nothing. And we wouldn't need to worry about modified Newtonian dynamics, or we could blend in modified Newtonian dynamics to some degree into the quantum dark matter theory, and together somehow that could actually explain dark matter. And then that would mean that there wasn't this something called ghost matter. It would simply just be regular normal matter that's been stretched so far apart that it's become invisible and does not interact with itself or with light or with anything except gravity. And that is roughly what I'm going to be talking about at the speech at the conference next year at Marimbula, buddy. Kanga, how you going? Kanga and Eagle are friends, by the way. They get along. And Eagle's like, oh man, I drink Corona. He's like, Corona, what's that? You gotta drink Tui's. Anyway, so we'll get to that one day. All right, guys, well, I'm going to stop YouTube and to say to those guys, it was a pleasure to have you. Someone's just said, I'm going to friend you so I can act a bit brainier to my friends. I do seem smart. I'm not sure if I am. We'll figure it out one day. All right, so YouTube guys, take life one smack at a time.